Hello, and welcome to Astronomy Daily. I'm Anna.
And I'm Avery. It's Monday, July 6th, and we've got a properly stacked show for you today.
We're talking a nail-biting asteroid flyby from Japan, a genuine cosmic mystery on two different worlds, and a hint that we might finally be hearing the universe's oldest ghost signal.
Plus, a black hole theory that could rewrite the rulebook, a look back at the weekend's aurora action, and a very long-range weather forecast for the edge of the solar system.
All that right after this.
Let's kick off in Japan, where Mission Control had a genuinely nervous Sunday night.
This is Hayabusa 2. Yes, the same spacecraft that brought samples back from asteroid Ryugu in 2020. It's been on an extended mission ever since because it turned out to have fuel to spare.
And on July 5th, Japan time, it did something it was never really designed to do, a high-speed flyby of a near-Earth asteroid called Torifune, passing within about 800 meters at more than 18,000 kilometers an hour.
800 meters at that speed. JAXA described it like trying to shoot a coin somewhere between Okinawa and Hokkaido.
The spacecraft's cameras were never built for a flyby like this. Hayabusa 2 is a rendezvous spacecraft designed to hover close to an asteroid for months, not scream past one in a heartbeat.
So this whole encounter is really an engineering demonstration first, science second.
And the reason it matters beyond the wow factor is planetary defense. If humanity ever needs to nudge a hazardous asteroid off course, we need to know how these bodies behave up close. Do they act like solid rock or more like a loose pile of rubble? That changes everything about how you deflect one.
JAXA confirmed the spacecraft is healthy, the flyby went to plan, and cameras captured imagery of Torifune's shape, texture, and temperature that scientists are poring over now.
Torifune itself is only about 450 meters across. No sample returned this time. This one's a look and go. Hayabusa 2's next big date is 2031, when it rendezvous with a completely different target, the small, fast-spinning asteroid 1998 KY26.
So think of Sunday as a dress rehearsal, a spacecraft already past its day job still finding ways to be useful.
Our next story is one of those lovely, we genuinely don't know what this is moments in astronomy.
Researchers combing through James Webb Space Telescope data have found an unexplained absorption feature, basically a dick in the light spectrum, sitting at exactly 5.11 micrometers.
And they found it twice, once on Saturn's big moon Titan and once on Pluto.
Which is odd because Titan and Pluto are about as different as two icy worlds get. Titan has a thick nitrogen-methane atmosphere, methane lakes, actual rain. Pluto has a wisp of an atmosphere and is bitterly cold and airbound in name only.
The team, led by Bruno Bazard at the Paris Observatory, checked whether the signal could just be coming from the atmosphere rather than the surface. And on Titan at least, the absorption was actually weaker at the edge of the disk, where you'd expect an atmospheric signal to be stronger. That points to the surface as the source.
They've ruled out the usual suspects: common ices, street-forward hydrocarbons, the nitrogen photochemistry products you'd expect. The closest match so far is a class of molecules called allenes, but it's not confirmed.
And here's the twist. On Pluto, the same absorption line
Is about 3 times broader than on Titan, even though it sits at the same wavelength. So whatever it is, it's behaving differently on each world.
This result is still a preprint, so it hasn't cleared peer review yet, but the researchers are calling it one of the more compelling unassigned features they've seen. Solve this one and you learn something new about organic chemistry happening in the deep freeze on two worlds at once. Next, Story 3 takes us underground, literally, to the Super Kamikonde neutrino detector in Japan.
Every second, somewhere in the universe, a massive star reaches the end of its life and collapses into a supernova. Each one of those explosions floods space with neutrinos, ghostly particles that barely interact with anything.
Physicists have long predicted that all of those neutrinos from every supernova across the entire history of the universe should add up to a very faint, constant background hum, the diffuse supernova neutrino background, or DSNB for short.
It's never been detected until maybe now. The Super Kamikonde collaboration presented results this week at the Neutrino 2026 conference in California. After combing through nearly 5,000 days, that's about 13 and a half years of data.
They found a statistically significant excess of events in the expected energy range. The confidence level works out to about 99.5%.
Which sounds enormous, but in particle physics terms, it's still short of the gold standard 5 sigma threshold needed to call it a discovery. So the team is very deliberately calling this an indication, not a confirmation.
Still, if it holds up with more data, this would be a whole new way of studying the history of the universe's supernovae, using particles instead of light. It could tell us how often massive stars have exploded over cosmic time, and how black holes and neutron stars formed.
A background hum from every dying star that ever lived. Not bad for a Monday.
Sticking with big theoretical ideas, Story 4 is a fresh attempt to solve one of physics's most stubborn headaches: the black hole information paradox.
Quick refresher. Stephen Hawking showed in the 1970s that black holes very slowly radiate energy and, in theory, eventually evaporate completely. The paradox is what happens to all the information about everything that ever fell in. Quantum mechanics says information can't just vanish, so where does it go?
A new theoretical study proposes an answer using a 7-dimensional model of spacetime, built on something called Einstein-Cartan geometry with torsion, basically letting space-time twist as well as bend.
The researchers found at extreme densities, right at the Planck scale, that twisting produces a repulsive force strong enough to halt the final stage of Hawking evaporation completely.
Instead of vanishing, the black hole would freeze into a stable leftover object, a remnant, with a predicted mass of around 9 × 10⁻41 kilograms, genuinely tiny.
And the proposal is that this remnant acts like a permanent archive, with the black hole's information encoded in long-lived internal vibrations rather than being lost.
It's squarely in fascinating but far from settled territory. This is a theoretical framework, not an observation. But it's a serious attempt to answer a 50-year-old question. And it comes with a neat bonus. The same geometry might also help explain why fundamental particles have mass in the first place.
2 birds, 1 7-dimensional stone. Next up, a quick check-in on the sky show from the weekend for anyone who missed it or is still out chasing it.
Saturday's X.1 solar flare and its coronal mass ejection slammed into Earth's magnetic field as forecast, pushing geomagnetic activity up to G3, strong storm levels through July 3rd and 4th.
Aurora borealis was reported as far south as Utah, Colorado, and Nevada in the U.S., with some lovely July 4th fireworks and aurora combo shots doing the rounds online.
NOAA's Space Weather Prediction Center says activity has been easing since, with conditions dropping to unsettled to G1 levels through today, the 6th, as the effects of last week's CMEs fade out.
So if you're in a high-latitude spot, southern hemisphere included, tonight's still worth a glance skyward. But don't expect a repeat of Saturday's fireworks. The main event has passed.
Our last story is a lovely bit of long-range weather forecasting. Except the weather is solar wind, and the destination is interstellar space.
NASA's New Horizons, the spacecraft that gave us our first close-up look at Pluto in 2015, and then flew past the Kuiper Belt object arXiv in 2019, is still out there, still working, currently around 66 astronomical units from the sun.
Researchers at the Southwest Research Institute, led by Dr. Jonathan Gasser, have combined solar wind forecasting with heliosphere models to predict when New Horizons will cross determination shock, the first plasma boundary marking the edge of the sun's influence before the true edge of the heliosphere further out.
Their answer? Somewhere between 2029 and 2040, which is, let's be honest, a pretty wide window.
But that's because the heliosphere isn't a fixed shell. It swells and shrinks with the solar cycle, expanding during solar maximum and contracting during solar minimum. New Horizons might even cross the boundary more than once if the shock front moves back and forth across the spacecraft's path.
For context, Voyager 2 crossed its termination shock back in 2007, at 84 astronomical units and measured a sharp 46% drop in solar wind speed right at the boundary.
If New Horizons gets there, it'll become only the third spacecraft in history to cross into that outer frontier, after Voyager 1 and 2. Not bad for a mission that was just supposed to visit Pluto.
A whole new frontier, and we might get to watch it happen live sometime in the next decade or so.
And that's a wrap on today's episode. An asteroid flyby, a shared mystery on two icy worlds, a possible whisper from every supernova that ever happened, a theoretical black hole afterlife, some leftover aurora, and a decade-long forecast for the edge of the solar system.
If you enjoyed the show, please do leave us a rating and review. It genuinely helps other space fans find us.
I'm Avery.
And I'm Anna. We'll see you next time on Astronomy Daily. Clear skies, everyone.